Hiya! So in this video, we're going to look at an example of the Poisson distribution using this idea from before where we might have multiple Poisson distributions and we're going to try to sum them up to kind of give an intuition of where this is kind of coming from. So first, let's kind of set up the problem. Suppose we're watching a game of bowling. So I don't know if you know bowling, but bowling is where there's the 10 pins at the end of a big lane. You take a ball and you throw the ball at the pins and you try to knock them down. If you knock all of them down, that's called a strike, and that's kind of the goal. So there's 4 players on a team. The first player has a 1/15th chance of hitting a strike. The second player has a 1/20th chance. The third player has a 1/70th chance, and the final player has a 1/10th chance of hitting a strike. So they each will throw the bowling ball 10 times and see how many strikes they get. What is the probability distribution for how many strikes the team will get as a whole? So I want to know as a whole. And here I'm saying use the Poisson, so I'm telling you explicitly use the Poisson distribution for each player and assume that each throwing of a ball is independent. So here I'm telling you use Poisson. So if I tell you use Poisson, you should probably use Poisson. Okay, so we're using Poisson. I'm given my parameters of 1/20th, 1/15th, etc. No, these are not the parameters, sorry. These are the chances, right? So I need to use I need to figure out my mu. So in this case, my mu is just NP, right? So I have 10 times P because they're each doing 10 things. And so here I have a 1/15th chance. So for example, mu1 is equal to 10 over 15. Mu2, this is going to be equal to 10 over 20. Mu3 is equal to 10 over 70. And mu4 is equal to 10 over 10. So why are we multiplying? So the question becomes, why are we multiplying here when we're not talking about the binomial distribution? And the reason why is because the Poisson distribution is for each individual roll. So what this means is when I sum up these things, Poisson for each roll, well, if I have P for each roll, well, I do 10 rolls, so I need to do P, or I guess mu, right? Mu is my parameter, mu, and I need to do this how many times? I need to do it 10 times, right? So I do this 10 times, so I do 10 times mu. So I have 10, yeah. So in essence, here, mu1 is really more, I guess P is not a good thing to write here. It's really just mu, right? This is our parameter. And this is where these numbers are coming from. And here again, we can just look at the sum. So if I look at S is equal to x1 plus x2, and this is really what we're asking here. What is the sum of all 4 players together, right? As a whole, we want all of them together. That means my mu, I can just sum up. So I can do mu1 plus mu2 plus mu3 plus mu4. And these we already have on the side, right? So this is 10 over 15 plus 10 over 20 plus 10 over 70 plus 10 over 10. And if we add these up, this gives me 97 over 42. I'll let you do the calculations there. But since we know, right, we're told that if I do this sum, I get a Poisson random variable with parameter this. This implies S is Poisson. And I want to calculate the expected number, right? What's the probability? Oh, what's the probability distribution? Sorry. So that means the probability distribution is just this. So S is Poisson. So S is a Poisson. So the distribution is a Poisson distribution with parameter 97 over 42. And that's it. That is our distribution. So that concludes this example. In the next video, we'll look at things called random scatters, which uses this Poisson distribution to kind of go a little deeper. And it's a fun little theorem, at least for me. I think it's cool. So I will see you then. Yeah, that's it. See you then.